Evening, guys. Are you able to hear me?
Yes, sir.
Okay. Now we'll continue with the topics of modulus of elasticity. So yesterday we saw two important points. What was it? We saw what is strain and what are the types of strains. So there are three types. We saw these three types. 1 minute. Yeah. So there are three types of strains that we discussed. One is longitudinal, second is volumetric, and the third is shearing. Right. So after that we saw the concept of moduli of elasticity. In moduli of elasticity, what did we see? Again, there will be three types. So what is basically modulus of elasticity? How do you define modulus of elasticity? It's ratio of something. What is it? It is a ratio of
Stress by
and
strain.
under what conditions? Within?
Elastic limit.
Yeah, you should never forget that. So within the elastic limit, the stress is directly proportional to strain. And the first type of modulus of elasticity that we saw is Young's modulus of elasticity. Right. So how was it defined? It was defined as longitudinal stress divided by longitudinal strain, and this is what is Young's modulus, right? The next concept that we are going to see is, what will be the next concept? You guys can guess it, right? So there is a pattern that is being followed in this chapter. After longitudinal, what have we been seeing? It is volumetric stress divided by volumetric strain. So this should also have a name, and the name given to this is bulk modulus of elasticity. Okay, this is what we call it as the bulk modulus of elasticity. Okay. Okay, these experiment and all are not needed. I'll tell you what are all the things that are not needed. Is not needed. The next question is bulk modulus. Okay. So within the elastic limit, the ratio of the volumetric stress to the volumetric strain is called as the bulk modulus. Okay. So how do we write bulk modulus? As volumetric stress is nothing but pressure, and volumetric strain is written as delta V divided by V, and there is a negative sign because I told you yesterday, volumetric strain is always going to happen when it is compressional. Right? It is a compressive factor. So this can also be written as P into V divided by minus delta V. Okay. And generally the bulk modulus is represented by the symbol K, and K is equal to minus of delta P divided by delta V into V. You can write it like that also, where delta P represents the pressure that is applied. Okay. So please make a note of this point. Now, an important point to be noted here is bulk modulus will exist for all states of matter, whether it is a solid, liquid, or a gas. And bulk modulus of gas is very low for solids, and it is very high for. Sorry, the bulk modulus of gases is very low, and the bulk modulus of solid is very high. Why is the bulk modulus for solid very high? Because you need more amount of pressure to be applied to compress it. Right. Secondly, gases are more elastic as they are more compressive, right? So the bulk modulus of solids is greater than the bulk modulus of liquid is greater than the bulk modulus of gases. So you can mark this as important. Okay. See, remember this concept. We will be discussing about this concept again in the last chapter that is called as waves. Okay. So I cannot explain the concept now because I need to explain what is isothermal and adiabatic process. And we need some mathematical expressions to be understood to support it. So as of now, I will just read it out, have it in your mind, but we will be discussing about this in depth in the waves chapter. So gases have two types of bulk moduli. What are they? One is called as isothermal elasticity corresponding to the isothermal change. Any idea of what is isothermal?
Constant temperature.
So iso means same. Yes, correct. Thermal refers to temperature here. So if any process is carried out at a constant temperature, we call it as an isothermal process. Any idea about what is an adiabatic process?
No heat change.
No change in
Heat.
Yes. That is no exchange of heat takes place. Right. For example, you would have taken these flasks for coffee, tea, and all those things, right? If you go for some picnic or something, right? In those things, what will happen? You can see that the beverages are still hot even after some time. How is it able to happen? Because the walls that are made are adiabatic. Okay. Next. As I told you, I'll discuss about this in depth at that point.
Sir, so
So
adiabatic condition is same as the of isolated system.
it's like an isolated system, yes. Isolated from the surrounding where you don't exchange heat. Okay. Yeah. So the next term that we need to see is compressibility. So what is compressibility? It is the reciprocal of bulk modulus. So the reciprocal of bulk modulus is called as compressibility, and compressibility is written as 1 divided by bulk modulus. Okay, have this point also in mind. Okay, so generally, if you want to define the compressibility for a rigid body and a liquid present in it, they both are compressible. Okay, sorry, incompressible. Hence, the compressibility for a rigid body is going to be 0. This might be a 1 mark question, right? So we have seen two types. What are they? One is Young's modulus, and the second is bulk modulus. The third type, what did I say? It is something related to shear stress and shear strain. I told you the name yesterday. It is called modulus of
Rigidity.
Rigidity.
yes. It is called modulus of rigidity because solids have the tendency to change their shape because shearing stress and shearing strain will cause something to the change in shape of the object. Right. So rigidity of modulus is also called as shear modulus or sometimes referred to as torsional modulus also. Okay. So within the elastic limit, the ratio of the shearing stress to the shearing strain is called as rigidity modulus, and it is written like this. Okay. So ratio of shear, 1 minute, shearing modulus, shearing stress. Shearing stress divided by the shearing strain is what is called as rigidity modulus, or we also refer to it as modulus of rigidity. Okay, having this point in mind, listen to this carefully. Suppose you consider a cube of side C. Okay, shown in the figure. When a force F is applied on the top surface and area, top surface face of area A, fixing its lower face. So the lower bottom is fixed. And the shearing force that you have applied is capital F. So what is going to be the shearing stress that it would undergo? Shearing stress is equal to F divided by A. Then what about shearing strain? Shearing strain
Theta.
is delta L divided by L. Sorry, not delta L. It is this displacement. Small l divided by the distance between the parallel surface, that is capital L. Yeah, as you told, it is theta only. So shearing stress divided by shearing strain will give us F into theta divided by A, or this is also equal to F into capital L divided by A into small l. Okay.
Sir,
So if you
should come
tell
in
me,
denominator, right?
huh? Which one?
Should come in denominator. Right?
Oh, sorry, yeah. F by A into theta. Yes. Now is it fine? So theta is equal to small l divided by capital L. Yes. So as I told you, modulus of rigidity, rigid substances are solids. So solids alone possess modulus of rigidity. Liquids and gases do not possess any rigidity modulus. Okay. Let us do a small problem to understand. There is a square lead slab. Lead is a material. Square lead slab of side 50 centimeter. So side is 50 centimeter and thickness 10 centimeter. Okay. And thickness 10 centimeter. It is subjected to a shearing force on its narrow face. So narrow face means on the surface, which is 10 centimeter. So the topmost portion, 10 centimeter, is undergoing a shearing force of how much value? 9 into 10 power 4 Newton. The lower end is riveted to the floor. So it is fixed to the floor. How much will the upper edge be displaced? That is what we need to know. So how to solve this? So small a is this much. So the lower edge is riveted. How much will the upper face be displaced? So we know that shearing strain is equal to this distance L divided by this distance capital L. So L divided by capital L, right? And what is the shearing stress it is undergoing? It is the force divided by area, right? But one minute, they didn't give anything about the modulus of rigidity, right? Then in this question, one data is missing. That is the modulus of rigidity. Neta value should be given. See, modulus of rigidity is represented by this symbol. I didn't tell you what this symbol is. This is called as neta. It's a Greek letter. Okay, NETA. So the modulus of rigidity of the lead material is actually 5.6 into 10 power 9 Newton per meter square. So it is 5.6 into 10 power 9 Newton per meter square. Don't worry, this kind of a mistake will not happen in your exam. Right. Now, since you know the value, what can you do? You will write neta is equal to shearing stress divided by the shearing strain. So shearing stress is force divided by area. Shearing strain is L divided by capital L. This L is what we need to find, which implies neta is 5.6 into 10 power 9 is equal to force given is 9 into 10 power 4 divided by area is how much? Area on which this force is being applied is how much? So on which side is the force being applied? It is this side. So area of this side is how much? So area, 1 minute.
0.05.
Yeah. So it is going to be 50 multiplied with 10. So 50 into 10 into 10 power minus 4, the whole divided by small l divided by what is the value of capital L? That is 50 again. That is 50 because that is it.
Multiplying 50 into 10, sir.
See, that is what even I'm thinking. There is a square of side 50 centimeter. There is a square lead slab. This side is 50 means it's a square lead. So this side is also 50 only. No? You're able to understand. I will shade it with red color pen. Observe that is having a square side. This part is a square side. That's what they told. No, square lead slab. So this is 50. How much will this part be? That is this part. This is also 50 only. No, that is why 50 multiplied with 10 will give you the answer for this area. Are you clear?
Sir,
Yes or no?
find the area of square, right, sir?
No. See, you read the question carefully. There is a square lead slab of side 50 centimeter and it has a thickness of 10 centimeter. Correct? It is subjected to what force? Shearing force on which side? On its narrow side. Out of 50 and 10, which is a narrow side?
10, sir.
That is why it is that side is 10. So the top portion, this length, is of 10 centimeters. Okay. So that is why we are multiplying with 50 into 10 divided by capital L is how much? 50 into 10 power minus 2. So 50 and 50 are gone. 10 power 3. So 9 into 10 power 3 divided by 10 power minus 2. So 9 into 10 power 5. 5 point divided by small l. So small l will be equal to how much? Did anyone get the answer? 9 into 10 power 5 divided by 5.6 into 10 power 9. So it should be 1 point something into 10
Sir,
power minus
1.61 into 10 power minus 4.
1.61 into 10 power
Yes,
minus
sir.
4. It is in meter only, right?
Yes, sir.
Yes. So 1.61 into 10 power minus 4 meter, or you can write it in millimeter also. 0.16 into 10 power minus 3 meter, which is going to be 0.16 millimeter. So look at the modulus of rigidity. 5.6 into 10 power 9 times. It's almost giga. Right? Those many times it has the modulus of rigidity. That is why, in spite of applying a force of 9 into 10 power 4 Newton, look at the displacement that has caused to the top surface, which is even 0.16 millimeter. Less than 2 millimeters. You're able to understand?
Sir, I couldn't understand that area, sir.
Okay. See, there's there. Is it a cube or a cuboid?
Cube.
A lead square slab is given. They didn't say it's a cube. There is a square lead slab. So there is a square lead slab. Square means it is going to be something like this. Right? Where this is 50, this 50 accepted.
Yes, sir.
And its thickness is 10 centimeter means it is projected towards you like this with a value of how much?
10.
So this is 10 accepted.
Yes, sir.
Okay. Now, how did they keep it? They kept it in such a way that the force is applied on the narrow surface. So out of all the permutations combination, which surface is narrow? Like one of the sides is 2500. The other side is having an area of 2500. There is one side which has an area of 500. Which one is the narrow one?
The topmost.
That's what is happening. That is why we multiplied 50 with 10.
Okay, sir. Got it.
Got it? So the next concept is Poisson's ratio. Okay, this has something to do with the wire when it is stretched with the help of a tensile, when it is undergoing a tensile stress. So when a wire is stretched with the help of tensile stress, that is when two equal and opposite forces are applied to a wire along a certain direction, the wire extends along the direction. Correct? Are you able to understand?
Yes, sir.
So this is a wire. A cylinder in a two-dimension will appear like a rectangle. Okay. If you want, I will draw it like a cylinder also, because when you say it's a wire, it's going to be something like this. So this is its original length. Now, when force is applied from both the sides at certain direction, what will happen? It will get elongated. So when there is an extension that is taking place, correct? When there is an extension of delta L taking place, what else will happen? There will be a decrease in diameter. Is this not the right diagram? I'll draw it again. Listen to this carefully. So when when a wire is subjected to tensile stress, sorry. Delta L is increasing compared to its original length L. There is a decrease in this diameter also. Delta D is taking place. Are you able to understand? So this is what happens when a wire is actually subjected to a tensile stress. Now, from this, there are two other new terms that are going to come. Listen to them. What can? The wire extends along. The wire extends along what? The wire extends along the direction in which you applied the force, right? At the same time, it also contracts along the perpendicular direction. That is, its diameter will get contracted. So if you are able to calculate the fractional change like this, the fractional change in direction along which the forces have been applied is called as longitudinal strain. Means if you are able to calculate delta L by L, we call it as longitudinal strain because it has appeared along the length. This is already a known fact. But there is a strain that is happening perpendicular to the length also. That is delta D by D. Then what is the name given to this? Then what will be the name given to this? This is what we call it as lateral strain. Okay. So I read the statement again. The fractional change in direction along with the forces have been applied is called as the longitudinal strain, while the fractional change in the perpendicular direction is called as the lateral strain. Okay. So one thing that is observed is lateral strain is directly proportional to the longitudinal strain. Obviously, right? If the length is going to increase, the diameter, the thickness has to keep decreasing in such a way that the volume of that material has to be a constant. So lateral strain is directly proportional to longitudinal strain. And if you remove the proportionality symbol, the constant that you introduce is sigma. You would have seen this sigma and you would have seen this sigma. Okay. So this is also sigma. Remember that this is also sigma. And here the sigma is what represents the Poisson's ratio. So how do you define Poisson's ratio? It is defined as the ratio of the lateral strain to the longitudinal strain. Right? The ratio of the lateral strain to the longitudinal strain is called as the Poisson's ratio. Okay. So for the expression, I will show you a small derivation. So consider a wire of length L and diameter D. By fixing one end of the wire, a force F is applied at the other end parallel to its length. So what will happen? So the wire is fixed at one of the ends and it is subjected, let's say its original length is L and it is subjected to a force. Then what will happen is its diameter will decrease and length will increase. So Delta L by L, I call it as longitudinal strain. Delta D by D with a negative sign is called as the lateral strain. If you take the ratio of delta D by D to delta L by L with a minus sign, that is what is called as the Poisson's ratio. Are you able to understand? So Poisson's ratio is an elastic constant for a wire. Obviously, it has no dimension because it is a ratio of strain to strain. And the value of sigma will lie between -1 to half. These are the theoretical limits. So you need to have this in your mind. Okay. So practically, when you speak, sigma lies between 0 to half. So you obviously, I'm hoping that you would have understood what the negative sign indicates. The negative sign indicates that the diameter of the wire decreases if the length of the wire increases, and the vice versa. Right, guys? Any doubt? So this is all about Poisson's ratio. So are you guys there first of all?
Yes, sir.
Yeah. Next. So these things are again not needed. These are not needed for CBSE. So the last but one concept that we need to see is behavior of a metal wire under increasing load. This is what we call it hyphen strain curve. Okay. So when you take the stress here and the strain here, we will be plotting a graph observing how an elastic material responds to the given stress. Okay. So to study the behavior of a metal wire under increasing load, a metal wire is clamped at one end and gradually loaded at the other end. The same logic, it is clamped at one of the ends and it is loaded at the other end, so that the weight of the object is responsible for the elastic material to increase its dimensions. So the load is increased until it breaks. So what they will do, they'll keep changing the value of mg, okay, until it breaks. So during this process, there were certain things that were observed and the graph was plotted. Okay, so a graph is plotted between the stress on the y-axis and the strain on the x-axis. In general, the curve shown in the figure, which is also called as the stress strain curve. Okay, now listen to this carefully. So how is stress and strain related within the elastic limit?
Directly proportional.
Yes. So can I say stress is equal to E times strain? So E will be equal to stress divided by strain. Everybody has learned straight line chapter. So stress is taken on y-axis, strain is taken on x-axis. Then how is it behaving? Is it not behaving like the slope of the line? So what does y is equal to mx represent? It is a straight line passing through origin. Right. So initially what will happen is the graph will be increasing in proportion till a point called as P. Okay, till a point called as P. So in the graph, OP is a straight line showing the stress is proportional to strain. That is, the wire obeys Hooke's law up to the point P. So what is that point P called as? It is the limiting value, elastic limit, and it is also called as the proportionality limit of the wire. Okay, so these are all different names. Okay, now suppose they give this kind of a graph and ask you to, let's say they are giving you certain values. Okay, let's say they gave you the value as 0, sorry, not 0. They gave you the value as 1, half, and they ask you to calculate the modulus of elasticity. How will you calculate it?
Take the ratio.
Yes, slope is what? Half minus 0 divided by 1 minus 0, which should be half. So the slope is mathematical term, and in terms of physics, it is called as the modulus of elasticity, provided it is within the elastic limit. I hope I'm clear with that point. Right. Now, if you increase the load slowly beyond the point E. Then you can observe from P to E, there will be a small bend. It's slightly curved, which we can't see here, which is slightly curved. The stress is not proportional to the strain. So because, what did we say? Stress and strain are proportional, it should only form a straight line. Whereas whenever the curvature is taking place, no more linear equations are going to work, right? So stress will not be proportional to strain. Then what will happen? If the load is removed at any point O, any point between O and E, what will happen? The graph is slightly curved. The stress is not proportional to this thing. I'm sorry, it's repeating again. If the load is removed at any point between O and E, it will regain its natural length. Okay, this point E is what is called as the elastic. So there is a slight curve. Are you able to understand? So the point P is called as the proportionality limit and E is called as the elastic limit. So this curvature means anywhere between these 2 points O and E, if you remove the load, what will happen? The material will regain its original shape. Here it is the wire. Okay. So in case of some materials, the wire may obey Hooke's law up to point E, coinciding E with P. That is, P will be the elastic limit for such materials. So here we are discussing about what? We are discussing about a metal wire. Okay. So after this elastic limit, what do you think will happen? On increasing the load beyond the elastic limit, the graph is more curved up to the point Y. So graph is more curved up to the point Y, where that Y is called as the yield point. Okay. So what can we say after the elastic limit from E to Y, that is from the elastic limit to the yield point, what can we say? The wire does not behave any Hooke's law, indicating that for small increase in load, there will be a greater increasing in length because it has started losing its elastic property. So if suppose you have reached anywhere between E and Y, let's say the load is such a way that the graph is falling somewhere between E and Y. On removing the load, what is going to happen? The object will fail to regain its original shape and size. Okay. From E to V, the wire does not obey Hooke's law, indicating that for a small increase in load, there is a greater increase in length. So please underline this. Very, very important. Okay. If the load is applied on the wire, is removed anywhere between E and Y, the wire does not regain its natural length completely. It will have a permanent increase in length. This behavior of wire is shown by the dashed line, which is a straight part that cuts the x-axis not at O but at O dash. Hence, OO dash is called as the permanent set. Means what will happen? Try to understand this point. So if you remove the load somewhere over here, I'm using a light blue color. See, if you remove the load somewhere over here, the material will retrace this path and come to point O. Okay, if you do it here, it will retrace. If you do it at point E, it will retrace. But if you do it somewhere between E and Y, what will happen? The material will no more retrace this path. Rather, it will follow a new path and come to this position. And this distance OO dash is what we call it as permanent set. Means the length of the wire has increased from its natural length. Okay, there will be a small variation. Hence, OO dash is called as the permanent set. Okay. Next. After you cross the yield point, what will happen? When the wire crosses the point Y, the strain increases rapidly without any increase in the load. Okay. So yield point is defined as the point. Okay. So yield point is defined as the point beyond which strain increases rapidly without any increase in load. So beyond the point Y, as the wire becomes thin, the stress for the same load becomes larger and larger, increasing the strain further and further. So if the load is not removed, the strain increases continuously till the wire reaches a point T. Okay. So the stress corresponding to T is called as the tensile strength of the given material. The stress corresponding to point T. So stress means from point T, if you drop a perpendicular, this distance is what is called as tensile stress. Okay. The stress corresponding to point T is called as the tensile strength of the given material. The tensile strength is the ratio of the maximum load to which the wire may be subjected by slowly increasing the load to the original area of cross section of the wire. So it's the same as the tensile stress formula, right? It is a ratio of maximum load to which the wire may be subjected by slowly increasing the load to its original area of cross section, to the cross sectional area at which you started with. So what is happening beyond the yield point, there will be thinning of that wire taking place. And even for a small increase in the value of load, there will be a greater amount of strain that is getting subjected to the material. So beyond the point T, what will happen? The thinning of the wire is no longer uniform and the wire shows necks. Okay. Immediately as this occurs, the stress decreases automatically and the part TB is obtained. And the point B, as the name suggests, it is the breaking point. So at point B, the wire will ultimately break. Next in the sense, it is bend. I hope everyone is clear, right? Why is the class so silent?
Yes, sir.
Clear, right? Okay. So if large deformation occurs between the elastic limit and the breaking point, the material is ductile. Right? If the deformation between the elastic limit and the breaking point is very small, or if the wire breaks immediately after crossing the elastic limit, it is brittle. So you know what is ductile, right? What
Yes,
is
sir.
it?
Thinning of wires.
Yes, which can be drawn into thin wires. Brittle is something that can be broken easily. Okay, like as I told you at the beginning of the chapter, every material will possess some amount of elasticity. So this graph is one of the measuring parameters for us to understand whether a material is ductile or brittle. See, obviously in real time, we'll not sit and draw the graph. We will try do a testing and see. But theoretically, yes, we need to understand that this is what is going to happen. If you have to do an experiment and find out whether the material is ductile or brittle, this is what you do. Okay, this is also not needed. I'm cancelling all these things because they're not a part of CBSE. Okay. The last concept that we need to see is energy possessed in the wire, which we also call it as elastic potential energy. This is also not needed. Not needed. But if they teach you in your school, then let me know, then I'll explain. Okay, I'm trying to eliminate them only from the CBSE point perspective. So strain energy is the last topic, which is also called as the elastic potential energy. Right. See, this we discussed yesterday. Suppose you have an object. When an object is deformed, right, what will happen? The internal particles are disturbed from their equilibrium position. When that is going to happen, it is going to have more amount of energy possessed within it. So internal forces develop in direction opposite to the deforming forces. Hence, in the process of deforming a body, work has to be done against what? See, suppose there is an object like this, and it is made up of particles. All these particles have a position, and due to that position, they possess some internal energy, right? But if you want to change the shape of this object, you obviously need to apply a deforming force. So when you apply a deforming force, what is going to happen? We are saying that the object is going to change its shape. So when the object is changing its shape, can I say that the particles, the internal particles location is also changing as a result of which energy is possessed by them? So when you're applying a force, aren't you doing some work in causing the displacement of the particles from their original position? Right? So this work that you do will get stored in some form of energy. In this case, it will get stored in the form of elastic potential energy, but more appropriate word is strain energy, because The material is undergoing a strain. Okay. So if you're able to calculate the work done, that will mathematically give you the value of the strain energy. That is what we are going to see. So now read the statement. Hence, in the process of deforming a body, work has to be done against these internal forces. Thus, the potential energy of the object is increased. This is called as the elastic potential energy or strain energy. Right. So let us see how to calculate the expression for strain energy or work done in stretching a wire. So what should happen? Let us say you're considering a wire. Again, here we are calculating the elastic energy, elastic potential energy for a wire only. Please have this in your mind. Right. So if you consider a wire of length L and area of cross section A fixed at one end, and it is stretched by an external force applied at the other end. The force capital F is so adjusted that the wire is slowly stretched. Slowly stretched in the sense it is not stretched at a single shot. It is slowly pulled so that at every value, it undergoes a small displacement of delta x. Okay, that is the meaning of slowly stretched. Let y be the Young's modulus of the material of the wire. Let y be the Young's modulus of the material of the wire. Let the extension be dl. Okay, so wire is like this. It has a total length of capital L. The force is applied in such a way that how much is the displacement that has occurred for the time being? It is dl. So this force has caused a displacement of dl. So when the displacement is very small, can I say that small amount of work that is done is dw? So dw will be equal to F into dl. Any doubt till this step?
Sir, why are we stretching it slowly?
It is because if you do it fast, right, then kinetic energy should be taken into consideration.
Okay, sir.
If you do it fast, you need to take the kinetic energy of the particles also, right?
Yes, sir.
That is the reason why we always do the experiments slow. Okay. So let y be the Young's modulus of the material of the wire. Let the extension be dl. So this is going to be the small amount of work that is being done. Okay. Now I take this as the reference. I call this as 0 and I call this distance as L. The extension I call it as small l. The original length I call it as capital L. Okay. So what are all the parameters that are given? They have given Young's modulus, length, small l, and F is given. Okay. Now see what is going to happen. dw is equal to F into dl. But how can you write F in terms of Young's modulus? dw, can I write it as F? Can I write it as y is equal to F by A divided by small l divided by capital L? Correct? So F will be equal to y into small l divided by capital L into A. 1 minute. Into A will come here. Right? So y into A into small l divided by capital L into dl. I hope everybody is writing along with me. So y into A into small l divided by capital L into dl. So this is the value of dw, right? Now you observe you have dl, which is a differential coefficient, and a variable L, right? Now, if I take the total work that is done, I need to integrate it from where to where? Y A L into dl divided by capital L from 0 to the maximum elongation L. Okay. Y A into L into dl divided by capital L. So there is a mistake here. It is capital A that should be there. They changed it as small a. Okay, follow my steps. So what can be taken out of the integral? Y A divided by capital L into integral of LDL from 0 to L. Can I do this? This will be YA L square divided by 2L. Because integral of LDL is L square by 2. And between 0 to L is L square by 2 only. So YA L square divided by 2L is going to be the amount of work done. But what is this amount of work done that is going to get stored? This is what is the strain energy. YA L square, that is small L square divided by 2L, where smaller is the maximum elongation, capital L is the original length, and this is what is going to be the strain energy. Okay, so this will be half into YA into L divided by 2 times L into small L. Can I write? Sorry, 2 is already written. Divided by capital L into L. Can I write it like this? Now this YA into L divided by capital L. What is this? This is the stretching force. So can I write it as half into stretching force into what is this small L? Maximum
Elongation.
maximum elongation. Right. Did everyone copy this? Any doubt in any of these steps?
Sir, why can't we write L by L? No, sir, never mind, sir.
Okay. Right. Is this done? So this is all about the strain energy. So if somebody asks you what is strain energy, you should say half into stressing force into elongation. Now the question is, if I have to calculate the amount of work done per unit volume, then how are we going to do? That is half into force into elongation, the whole divided by. What is the volume of the wire? If I take a wire, yes, where A is the cross-sectional area, L is the length of the wire. So capital A into capital L. Right. So half into, can I write it as F divided by A into L divided by capital L? So half into, what is F by A? Stress into, what is small L? Elongation divided by original length. It is strain. So half into stress into strain is what we can call it as the amount of work done per unit volume. Am I clear, guys?
Can you scroll up?
Sure. Till where?
Right here.
This is fine?
Yes, sir.
Okay. Just a minute, guys. Just a minute. Right. With
Sir,
this,
is
this chapter.
work done and elastic potential energy the same?
Yes. See, remember only one thing. Whenever you read about energy, right? Whenever you read about any formula of work done, throughout science, not only in physics, throughout science, wherever you read, no, the first thing that should come to your mind is work done. Because the science works like this. Whatever work you do on a system, or whatever is the work done by a system on us, will always get stored in some form of energy. So energy directly doesn't have any formula. That is why the energy's simplest definition is capacity to do work. You're able to understand? So always, whether it is potential energy, whether it is kinetic, I think you asked me a question yesterday related to energy, right? So whenever you're talking about energy, I would rather suggest you to go with understanding, clear understanding of work done. And whenever you do work done, you need to understand work done by which force. If you have clarity of these two things, right, then you will have a better grip of energy. Okay, so that's it. So
Sir, here
to
we
answer
are
your question,
integrating because the force is variable.
yes, force is variable because force is a function of L. Correct? So F is equal to YA into small l divided by capital L. That means as the elongation keeps increasing, what will happen to the force that you're applying? It will also keep varying. That is what they're meaning.
Sir, I have one more doubt.
Tell me.
Sir, why can't we apply center of mass concept here?
Which mass concept?
Center of mass. We can
Here,
assume that yes, sir, the mass is concentrated at the center.
okay.
And now
You can do that. You can do that.
okay, sir.
You can do that. Maybe you're trying to find out something like, but you can see. You're trying to say that mg is concentrated here, right? It will be at the center of the wire. This is what you're trying to do.
Yes, sir.
Capital L. Then mg into, you need to calculate the displacement that it is causing. So L, right? So it should be mg into L divided by 2. Let me try and see. Because it is something we are inventing here. So work done, what do you want to do? It is, you want to use work done formula only, right?
Sir.
Work done is equal to force mg. But one mistake that might happen here is the force exactly is being applied here. The object is not elongating, right? Actually, I'm sorry, you can't apply it. Because what is the logic? Mg is an internal force. It is its own weight. But here, what is the concept? The object is not getting elongated due to its own weight.
Yes,
It is
sir,
getting
understood.
elongated due to the deforming force.
Okay, sir.
So you can't use it. Right? So see, the applications of elasticity is given in your textbook also, last part. That part alone I'm leaving it to you because it's a theoretical thing. You can go through it and you can approach me for doubts. Apart from that, I've dealt all the important concepts that are needed. Okay. So what I will do is I'll be sharing an assignment. You work on it in the next class. Okay. In the next class, what I will do is I'll help you with the doubts from the assignment for the first 20 minutes. Then we will move on to the next chapter, that is mechanical properties of fluids. That is more important. Okay, mechanical properties of fluids. It is a very, very big chapter and it takes some extra time. It is not as small as this.
Sir, can you scroll up?
Sure. Which page you want me to go?
Sir, a little down.
Little down. Tell me.
There.
Okay.
I have to check.
You are copying it, huh?
Yes.
Okay, do it. I thought you had some doubt. Is everyone else clear, guys? No other doubts, right?
Sir, could you share this material?
Yeah, do it immediately. Yesterday itself you asked, but I thought I'll share it after I complete this chapter. I'll do it today.
Okay, sir. Thank you.
Okay. Okay, if you don't receive it in next 10 minutes, just give me a reminder.
Okay, sir.
Okay. Yeah. That's it, right? Yeah.
Sir, I have one more doubt.
Please tell me. 1 minute before you ask your doubt. 1 minute. Guys, don't leave. There is a Google form that is sent in the group site. Please fill it up. Please fill it up immediately. It will take only 2 minutes. It is regarding the discussion we had yesterday. I want everybody to fill that Google form immediately. Okay, once the class is over, do that as the first thing, then you attend the next class. Yeah, Raghav, please proceed.
There is tension divided by area equal to the breaking stress.
Which tension?
For example, we are given a system
Okay.
where we are pulling two boxes which are tied together by a rope, and then we are asked to
Okay.
find the breaking stress.
Okay.
So should we find the tension and equate it?
Actually, you need to find the force due to which that breaking point is occurring. That is what the graph told us, right? Maybe if in the case that you're taking tension itself is sufficient enough to break, yes, then you should take tension divided by the initial area. Okay, the question is which area I should take, whether should I take the area at the time of elongation or the original area that I considered when the wire was fresh enough. You're able to understand? So this, I can't say that it is completely tension divided by area unless I know what is the force which is responsible for the breaking to happen. Okay, we can't just like that conclude.
Only tension is acting on the system.
Only tension is acting, but we don't know the elastic parameters involved, right? We didn't do any load test on it and check. But what is the stress strain graph telling us? You need to first cross the proportionality limit, then you need to go to the elastic point, then you need to go to the yield point, then you need to go to the tensile strength, then comes the breaking stress. Right? So unless I know what kind of a material it is, we can't comment anything. But if suppose, to answer your question in a precise way, if you are trying to say that tension is the one which is responsible for the string to break, yes, in that case, you will take tension divided by the initial area. Provided that material is a brittle material, means it is immediately getting broken without undergoing any elastic properties.
Sir, one more example, like if you want to find the breaking stress for an elevator, so that tension would be applied.
For the elevator's string that is connected at the top.
Yes, sir.
The one which is moving, right? The helping the lift.
Yes, sir.
Okay. For that, what do you want?
In case we needed to find the breaking stress for that, we need to do the tension divided by area, right?
We need to do tension. See, that is actually not as simple as how you state. If that is the thing, everybody in this world can construct an elevator. That's not how it works. It depends on the chemical properties and the physical properties of what material you choose. You're able to understand. So it depends on what material is used there. If you see, there'll be some twisted wires which are used, which will have a greater strength. They'll be so thick. I'm not sure if you have seen above the lift. If you get a chance at any point, you see a lift getting repaired or something, I would suggest you to see, or else go to YouTube and have a look of what is exactly present on top of an elevator. So it is not like just tension by area. Okay, you're trying to say that string which is there is completely strong. The tension, if you're able to overcome the tension itself, it is going to break. Is that what you're saying?
Yes, sir.
I'm trying to understand your question. Like, how are you? I want to understand your perspective to answer this. What exactly is running in your mind? Are you trying to say there are two strings? Let's say they are holding the lift elevator. Okay. You mean to say that the weight, there will be a limit, right? There will be a maximum load capacity beyond which you would have seen that it will ask people to step out.
Yes, sir.
Right. So if that
in case we needed to find that, how do we do it?
How do we do? Means, see, it depends on this material and the load that you're getting suspended. I told you, right? It depends on the nature of the material. For that also, you need to that material needs to undergo the stress strain curve graph. So a prototype or something should be designed based on which you try to do the stress strain graph test and observe at what point it is going to get broken. You're able to understand. So it is not like I can directly tell you that it is going to be tension divided by area.
Okay, sir.
Okay, this is a slightly tougher concept. Good that you have asked, but don't think much about it. With time and maturity, you will understand. Okay, that's it.
Sir, where is the Google form shared?
Sorry?
Where is the Google form shared?
It is there in physics group and math group as well. If we can fill it once. Okay, you can fill it once.
Then where it is, sir? It's not there, I think.
See, did you get the schedule which I told? I showed a schedule yesterday, right? Some yellow color sheet in which I showed you that this is how the schedule will be.
Yes, sir.
Along with that, did you receive a Google form?
No, sir.
No. Okay, I'll send it across. Okay, I'll ask my team members to send it. You'll receive it now. Once you receive it, right? Fill it off.
Okay, sir.
Okay. Yes, guys, we can wind up.
Thank you, sir.
Thank you, sir.